It is July 15th, 2022, and 57 years ago today, in 1965, Mariner 4 was closer than any spacecraft had ever come to our planetary neighbor, Mars. Mariner 4 sent back the first images of another planet ever returned from deep space, even though that required the help of a few items from an arts and crafts store. Mariner 4 redefined our understanding of the red planet. It changed our strategy for exploring Mars, but it also set the stage for further missions, not just to Mars, but to Mercury, Venus, and even the outer planets. It is history that deserves to be remembered.
The roots of the Mariner program can be tied specifically to the 1958 launch of Explorer 1, the first artificial Earth satellite launched by the United States. Tracking the satellite required a global communications network, and the Jet Propulsion Laboratory, which had been under the auspices of the Army since 1943, created a network using portable radio tracking stations in Nigeria, Singapore, and California. In 1958, the JPL was transferred to NASA as the nation sought to consolidate its various space exploration programs under a single civilian entity. One of JPL's primary responsibilities was the design and execution of lunar and planetary exploration programs using remotely controlled spacecraft, and it followed that NASA should create a single communication system that would accommodate deep space missions rather than having each project design its own system. This was initially called the Deep Space Instrumentation Facility, or DSIF, but would later be called the Deep Space Network. The network required 3 facilities, separated by approximately 120 degrees of longitude. That meant that as the Earth turned, a spacecraft was always above the horizon of at least one station. The network included 3 stations, one each in California, Spain, and Australia. As the construction of the DSN progressed, JPL started planning for missions to take advantage of the system. Additionally, NASA was about to gain significantly more capability for launching deep space missions with the introduction of the Atlas rocket system, a liquid-fueled rocket system originally developed for intercontinental ballistic missiles that was first introduced in 1957. The combination of the Atlas rocket and the DSN allowed new capabilities, and in 1960, JPL began planning for a series of robotic interplanetary probes to explore the inner solar system. According to an official NASA history, the project was named Mariner based on a naming convention suggested by Edgar M. Courtwright, Assistant Director of Lunar and Planetary Programs. Under the Courtwright system, the names of planetary mission probes were patterned after nautical terms to convey the impression of travel to great distance and remote lands. Interestingly, the Mariner program overlapped the Pioneer program. The exploration vehicles of the Mariner program would be small, each weighing less than half a ton. Their general design would include solar panels, which would be pointed towards the sun, and a dish antenna that would be pointed towards the Earth, and each would carry a number of scientific instruments. Representative of the reliability of space exploration and launch vehicles at the time, the Mariner missions were planned in pairs. That is, JPL explained in a fact sheet entitled Mariner to Mercury, Venus, and Mars. Each of the Mariner projects was designed to have 2 spacecraft launch on separate rockets, in case of difficulties with the nearly untried launch vehicles. Mariners 1 and 2 were intended to make planetary flybys to investigate Venus. The probe's launch was coordinated to take advantage of a window that opens every 19 months, in which Venus and the Earth reach relative positions in their orbits around the Sun, such that a minimum of fuel is required to travel from one planet to the other. The imperative to meet this window required rushed planning, and NASA was not able to make the launch window in 1961. This allowed the Soviets to beat NASA to the punch with the Venera 1 probe. While Venera 1 became the first probe to fly by Venus, the probe's communication systems failed, and it was unable to transmit any data on the planet. Mariners 1 and 2 were developed from the probes used in the Ranger program, probes designed to photograph the surface of the moon. They were designed for a weight of 447 pounds, or 203 kilograms, and would include 2 solar panels, or wings. The probes carried several scientific instruments, but no camera, as Venus is surrounded by bright, opaque clouds that hide the planet's surface. Mariner 1 lifted off on July 22, 1962, and almost immediately the rocket veered off course. This offered a potential hazard to populated areas, and according to NASA, because of a launch vehicle deviation from the planned flight path, Mariner 1 was destroyed by the range safety officer after approximately 290 seconds of flight. The failure was tracked to a software error in the guidance system. The $18.5 million probe was lost on a simple error, the omission of a single character in the software. But the loss was instructive, and new procedures as well as more durable computer programs were developed. The decision to have the missions designed in pairs turned out to be wise. The error was corrected, and Mariner 2 launched August 27th, before the launch window closed. Unlike Mariner 1, the launch went flawlessly, and the spacecraft successfully navigated a mid-course correction. On December 14th, 1962, Mariner 2 passed within 21,607 miles, or 34,773 kilometers, of Venus. Unlike Venera 1, the craft maintained communication, making the mission the first successful mission to another planet. In addition, Mariner 2 tested various engineering systems, such as attitude control, environmental control, and power systems, setting the stage for the next set of missions to Mars. This was not the first attempt to explore Mars. The Soviets had actually attempted 5 missions to the Red Planet, but all had failed. The Soviet Mars 1 spacecraft managed to fly by Mars in June of 1963, but by then had already lost communication and was unable to transmit any data. As before, 2 spacecraft were assigned to the NASA mission, which had the ambitious goal to photograph and return images of another planet. As with the Venus mission, the reason that 2 spacecraft were assigned was to account for the possibility that one of the craft might fail. The 574-pound, or roughly 260-kilogram craft carried 4 solar panels. Mariner 3 launched on November 6, 1964. While the launch seemed to go as planned, within an hour after launch it was clear that the ship's solar panels had not deployed, and the batteries were draining. Telemetry data suggested that a fairing, a launch cover for the instruments, had failed to separate, preventing the solar panels from deploying. Engineers tried to develop a solution to cause the fairing to separate, but ran out of time, and 8 hours after launch the probe's batteries failed. Even had they gotten the fairing to separate, the additional weight had already reduced the probe's velocity to the point where it would not have reached Mars.
Once again, the fragile nature of space exploration was demonstrated, and once again it proved prudent to have assigned 2 spacecraft to the mission.
The theory was that the fairing, or payload shroud's, inner fiberglass lining had separated from its skin, which then fouled the spring mechanism that was to have jettisoned the shroud. The solution was to create a single-piece, all-metal shroud, but this increased the spacecraft's liftoff weight, requiring more tweaking of the launch vehicle. Still, Mariner 4 was ready to launch in just 3 weeks, launching November 28, 1964. This time the shroud separated properly, and the craft was successfully on its way. In a last effort to beat the Americans, the Soviets launched the Zond 2 spacecraft just 2 days later, headed for Mars on an almost identical mission, including a camera. But the spacecraft lost attitude control during a mid-course correction and had lost communication. Meanwhile, the UPI reported Mariner 4 was setting records. As long as its radio keeps working, they wrote, every mile the Mariner 4 adds to its voyage through space, it sets a record for cosmic communications. The record it was breaking had been set by Mariner 2. While Mariner 4 did encounter problems, notably dust particles were occasionally reflecting light and confusing a navigation sensor that required lock on the star Canopus, used as a navigational point, engineers were able to correct the problem, and just over 7 months later, Mariner 4 approached Mars. Planetary data started to be returned on July 14th. Newspapers across America reported breathlessly. Since the 19th century telescope observations of Italian astronomer Giovanni Schiaparelli spied what he called canali, mistranslated in English as canals, there had been speculation of life on Mars. Mariner 4 would test that. The Honolulu Star-Tribune wrote, after 228 days in flight, Mariner 4 will pass behind Mars next Wednesday. Then comes the great moment. Will the camera work? Will the pictures get back okay? Will they answer the riddle of life on Mars? But getting those answers would take time. The camera would not start operating until the probe got closer, and then the data had to be transmitted. The UPI reported, for 12 hours, 33 minutes starting late today, United States scientists will taste the agony of waiting for a $5 million picture without knowing if the camera even worked. It was not just a matter of the camera and the transmission. The photos included too much data to stream directly. Rather, they were recorded on magnetic tape that would then be broadcast to NASA over time. The UPI continues. Whether the agony is sweet or bitter will depend upon what is on, or not on, a spool of recording tape floating in space, 134 million miles from Earth. And there was reason to worry. The tape recorder used was not originally intended to be used. It was a spare, pressed into service after the failure of Mariner 3, and some anomalous readings had suggested a possible problem with the tape. If the recorder failed, or sent some of the millions of bits of data incorrectly, much of the purpose of the mission would have been lost. This led to one of the most peculiar incidents in the history of space exploration. JPL's Dan Goods writes, after the failure of Mariner 3, NASA scientists and engineers at the Jet Propulsion Laboratory anxiously awaited the signals from Mariner 4's cameras during the final approach to Mars. There had been some anomalous errors pointing towards the tape recorder, and they had a right to be nervous, as the tape recorder on Mariner 4 was a spare, not originally intended for use. So Dick Grum, who oversaw the tape recorder, and his crew decided to prove that it was working, one way or the other. The issue was that even after transmission, it would take the NASA computers hours to process the image. Thus, Goods writes, while they were waiting, the engineers thought of different ways of taking the ones and zeros from the actual data and create an image. They decided that they could print out the digits of the raw data and manually color them based on how bright each pixel was. It was, in essence, a color by number that would demonstrate whether the data represented a picture or just a mess of useless data. But that required colors. Goods continues. So Mr. Grum went to a local art store and asked for a set of chalk with different shades of gray. The art store replied that they didn't sell chalk, but they did have colored pastels. Richard did not want to spend a lot of time arguing with them, so he bought the pastels. While it was an example of engineering ingenuity, it caused NASA's people some concern, Goods explains. The JPL PR folks were getting nervous that the news media would see the thing and not the actual pretty images. They told him to quit, but Grum argued that this was being done to confirm whether the instrument was working or not. So they allowed him continue if he did it behind a movable partition wall with armed guards around them. But armed guards were not enough. Eventually the media found out about it, and it got so excited the PR people couldn't keep them out. So it became the first close-up image of Mars to be seen on TV. That is, the first picture of another planet to be successfully transmitted from deep space was hand-colored. Today it hangs, Goods writes, in an out-of-the-way place at JPL.
The picture was representative of a mission that was an unqualified success. History professor Asif Siddiqui wrote in a 2018 NASA publication, Beyond Earth, the Chronicle of Deep Space Exploration, that the Mariner 4 mission was one of the great early successes of the agency, and indeed, of the space age.
Mariner 4's photos revealed a planet full of craters, ending the century-old speculation about previous civilizations on Mars. It determined that the planet's surface pressure was low, critical information for future landings on the planet. The images, Siddiqui concludes, fundamentally transformed the scientific view of the red planet, providing hard data where speculation had previously dominated. The success of Mariner 4 would set the stage for the rest of the expansive program, which returned to Mars and Venus, as well as to Mercury. The Mariner 4 mission occurred in the midst of the space race, among many missions by both the United States and Soviet Union, and yet it set itself apart in proving the capabilities of deep space exploration, a point underscored when the probe, originally intended to have a life of 8 months, continued sending data for 3 years, providing critical insight into solar wind and micrometeorites.
Because of Mariner 4, we know much more about our planetary neighbor, and our ability to successfully explore space was vastly improved. In the first pictures of another planet to be successfully sent from deep space represented a quantum leap in the human ability to extend our reach, and reach for the stars. And those pictures have special meaning to me, as they were taken as Mariner 4 made its closest approach to Mars on July 15th, 1965, which just happened to be my first birthday. History that deserves to be remembered. It is January 10th, and 54 years ago today, NASA's Surveyor 7 landed on the moon. It was the last landing for a program that was vital to America's Apollo program, the effort to place a man on the moon. The Surveyor program represented America's first successful lunar landing, and the some 87,000 pictures that were sent home from a Surveyor spacecraft dramatically improved our understanding of Earth's closest neighbor and only natural satellite. While the program is little remembered today, the Surveyor program was at one point a critical part of the Cold War contest called the Space Race that deserves to be remembered. The competition that would come to be known as the Space Race officially began in the summer of 1955, when representatives of both the United States and the Soviet Union publicly announced their national intent to launch artificial Earth satellites in the near future. The Space Race came to characterize the period called the Cold War. Competition over achievements in space exploration came to represent the competing economic systems and ideologies of the United States and the Soviet Union, with resulting national prestige affecting geopolitical conflicts, both hot and cold, throughout the world. The space race was certainly more than about science. The primary tools of space exploration, rockets, were the delivery system for nuclear bombs, as well as to place satellites with a host of applications, both commercial and military. In fact, among all the various interests driving national investments in space exploration, science was often pushed surprisingly to the back. And yet, almost despite itself, the scientific endeavor of exploration managed to accomplish actual science, with a host of Soviet and U.S. programs that studied the Earth, near-Earth planets, solar phenomena, and our closest neighbor, the Moon. A significant milestone in the space race came on October 4th, 1957, when the Soviet Union launched Sputnik 1, the world's first artificial Earth satellite, surprising the administration of Dwight Eisenhower. The concern raised in the U.S. over the Soviets beating the Americans into space has come to be called the Sputnik crisis. A preliminary evaluation presented to Eisenhower and dated October 16th concluded, public opinion will, for a period that cannot be forecast, be narrowly assessing the relative military positions of the U.S. and the USSR, and the USSR will, in this same period, have a clear advantage in the Cold War, which it can exploit for either peaceful gestures or ventures in increased pressures, or both, simultaneously. Perhaps most disturbing to Eisenhower was that the U.S. had the capability to launch a satellite much earlier, but chose not to. In a memorandum of a conference with the President dated October 9th, Donald Quarles, Assistant Secretary of Defense for Research and Engineering, admitted to Eisenhower that there was no doubt that had the Redstone rocket, being developed for military use, been used, the U.S. could have orbited a satellite a year or more ago. But, the Secretary explained, the Science Advisory Committee had felt that it was better to have the Earth satellite proceed separately from military development. One result of the crisis was a shift in how the U.S. pursued space exploration. On January 14, 1958, the director of National Advisory Committee for Aeronautics, the U.S. federal organization responsible for undertaking and promoting aeronautical research, wrote in a report that, it is of great urgency and importance to our country, both from our consideration of our prestige as a nation as well as military necessity, that the challenge of Sputnik be met by an energetic program of research and development for the conquest of space. It is accordingly proposed that the scientific research be the responsibility of a national civilian agency. In April, Eisenhower proposed the creation of a national civilian space agency that would take over the assets of the National Advisory Committee on Aeronautics, that would expand the organization's research role to include large-scale development, management, and operations. The agency thus created by the resulting act of Congress was the National Aeronautics and Space Administration, or NASA. A primary focus of the new administration was manned spaceflight. There was so much activity in space exploration between the launching of Sputnik and the first manned mission to the moon with Apollo 11 in 1969 that sometimes the multiple programs seemed to get lost in the mix, nearly forgotten by the societies who funded them. And one of those was NASA's Surveyor program, the first American spacecraft to successfully make a soft landing on an extraterrestrial body. Yet the $469 million program was at one point a critical part of the space race, and a necessary part of the process of trying to safely land a human on the face of the moon. The Surveyor program was highly impacted by another Soviet first. On April 12, 1961, the Soviet Union again surprised the United States and the world when it announced that it had launched pilot Yuri Gagarin into space, where he completed an orbit before being safely returned to Earth. The Soviets had beaten the objective of America's Mercury program. Newly elected President John Kennedy, who had been lukewarm on the priority of spending for space exploration, embarrassed by the Soviet successes as well as under political pressure following the failed Bay of Pigs invasion, decided that there was a political need for the United States to demonstrate our technical superiority in space. Consulting with Vice President Lyndon Johnson, who was chairman of the National Aeronautics and Space Council, NASA leadership, and other experts, Kennedy sought a goal in space exploration that there was a realistic chance the U.S. could achieve before the Soviet Union. The conclusion was that the U.S. had no chance of placing a station in space ahead of the Soviets, were unlikely to be able to have a manned mission to orbit the moon ahead of the Soviets, but the U.S. had a reasonable chance of being able to place a human on the moon ahead of the Soviets. Such a program, however, would be expensive. NASA Administrator James Webb estimated a cost of $22 billion. In May, the President proposed to Congress that the United States should commit itself to landing a man on the moon and returning him safely to Earth before the end of the decade. The nation was unconvinced. Many considered the space race to already have been lost. Others saw better use of the billions of dollars it would cost, and still others objected that the civilian effort was getting in the way of military development. Still, Kennedy's goal of placing a man on the moon before the end of the 1960s would direct national efforts. In a speech on national space policy at Rice University on September 12, 1962, he famously said, "We choose to go to the moon in this decade and do other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we are willing to accept, one we are unwilling to postpone, and one we intend to win." Kennedy's goal would have a significant impact on a program that NASA had started investigating the previous year. The Surveyor program had been started by NASA's Jet Propulsion Laboratory in the spring of 1960. It was an ambitious program that originally envisioned 17 missions to land robotic spacecraft on the moon. Aerospace historian William Melberg explained in 2014, it was originally envisioned as a scientific probe designed to answer some of the long-standing questions about the origin and nature of the moon. Project Surveyor would include orbiters and landers, the former intended to map the moon in unprecedented detail, and the latter designed to investigate its surface. But the mission of the program changed with Kennedy's goal. Melberg continues, when President Kennedy committed the United States to a manned lunar mission by the end of the decade, Surveyor soon became a supporting player in the Apollo program, blazing a trail to the moon for future astronauts. The 2020 book, The Surveyor Program, The History and Legacy of NASA's First Successful Moon Landing Missions by Charles River and editors, explains the goals of the program. To prove that the lunar surface was a place where a landing could safely be made. To show that a spacecraft could reliably be launched from Earth and reach a defined destination on the moon. And to prove that guidance and descent systems could reliably and safely land a spacecraft on the surface of the moon. The first goal was more vexing than you might imagine. Melberg explains that his father, Frank Melberg, was responsible for the development of a sophisticated zoom lens for the Surveyor landers. He quoted his father, "I soon realized that nobody really knew what the moon's surface was like. I was told that some scientists believed the surface might be volcanic rock, rugged and hard. Others said that the material would have the consistency of Portland cement, powdery but firm, and a few thought that Surveyor might sink into 12 feet of loose dust." Thus, Surveyor was not just a test for landing systems, but a test of a fundamentally important question. Was the surface of the moon actually capable of supporting a spacecraft? Melberg continues, the experts were still arguing amongst themselves about what we could expect to find on the moon because the biggest telescopes on Earth were unable to resolve any detail smaller than 1/4 of a mile in diameter. In fact, Surveyor was not the first program intended to discover the nature of the moon's surface and determine whether it was suitable for landing a manned spacecraft. The $100 million Ranger program had started launching probes in August of 1961. Unlike Surveyor, the Ranger program was not testing capabilities of a soft landing. Rather, the Ranger probes would simply crash into the moon. While the probe would be destroyed on impact, before crashing it would transmit detailed, close-up images of the lunar surface. Rangers 7, 8, and 9 had successfully sent back photos of potential landing sites. But the photos weren't enough, as the Surveyor program notes. The pictures provided by the Ranger spacecraft were very helpful, but they didn't actually prove that it would be possible to land on the moon. While the photos showed that the potential landing sites were indeed flat and not craggy volcanic rock, Ranger could not answer the question of whether the surface was comprised of a layer of dust that might bury a spacecraft. Perhaps most distressing, though, was the fate of the first 5 Ranger probes. Probes 1 and 2 had suffered launch failures and burned up as they re-entered the atmosphere. NASA had lost control of Probe 4, which crashed without transmitting any pictures. Ranger 6 landed as expected, but the cameras malfunctioned. Rangers 3 and 5 had simply missed the moon altogether, leaving in doubt the Surveyor program's goal of proving that a spacecraft could reliably be launched from Earth and reach a defined destination on the moon. The Surveyor program was significantly more complex than the goals of the Ranger program. The Surveyor program was testing whether a spacecraft could be softly landed on the moon, intact. Of course, something that would be critically important if we wanted to send a manned mission, and something far more difficult than simply crashing a spacecraft into the moon. And yet 2/3 of the Ranger spacecraft had failed to successfully do even that. And then, as the mission was nearing its first launch, the Russians surprised us once again. On February 3rd, 1966, months before the first Surveyor probe was scheduled to launch, the Soviet Union announced that its Luna 9 mission had successfully made a soft landing on the moon and had transmitted back panoramic pictures from the surface of the moon. The Surveyor program notes this was devastating news. Many designers at NASA's Jet Propulsion Laboratory wondered if the Surveyor program was a step too far. And yet the Soviets, who most Americans thought were not as advanced in their technology, had already done so successfully. Were the Soviets actually closer to a manned mission to the moon than the United States? Certainly the imperative for a successful Surveyor launch was greater than ever. The launch vehicle for the Surveyor program was the Atlas Centaur. Each spacecraft weighed approximately 650 pounds, around 10 feet tall. The descent would be controlled by the burst of a solid-fuel retro-rocket and then by small hydrazine engines controlled by Doppler radar. The engines would cut out about 10 feet above the lunar surface, and the craft would glide down. Constructed of aluminum tubing, the tripod-shaped craft's legs included shock absorbers to absorb landing impact. Strain gauges sent telemetry back to Earth to assess the force of the impact. Each spacecraft could include a solar panel and a battery and were designed to be able to carry an array of scientific instruments, as well as state-of-the-art video camera capable of taking both 200-line and 600-line resolution pictures and other scientific payloads. The Surveyor program notes, to achieve a controlled descent to the lunar surface without human intervention while 250,000 miles away would mean taking 1960s technology to its very limits. The Surveyor spacecraft, in addition to representing an important step on the way to the Apollo missions, was at the time the most advanced vehicle ever created. Surveyor 1 was launched at 10:41 a.m. on May 30th, 1966. The program had faced significant technical obstacles. The program director for Hughes Aerospace, the contractor that had built the spacecraft, had told a reporter that odds were 1,000 to 1 against a successful landing. With NASA and the nation in desperate need of a success in the space race, the launch was picture perfect. And after a trip of some 250,000 miles, approximately 63 hours and 30 minutes after takeoff, playing live on national television, Surveyor 1 landed successfully, the first soft landing of an American spacecraft on an extraterrestrial body. Surveyor 1 transmitted a total of 11,240 photographs and acquired data vital to the Apollo program on the radar reflectivity of the lunar surface, bearing strength of the lunar surface, and spacecraft temperatures for use in the analysis of the lunar surface temperatures. While there was some question whether the craft would withstand the extreme temperatures of a single lunar night, it continued to send and receive data well past its anticipated lifespan, until January 7th, 1967. America and NASA had an unqualified success on live television. Surveyor 7, the last of the Surveyor program craft, landed 54 years ago today. Despite some difficulties with equipment, the craft was able to conduct all its experiments, including surface sampling to determine the major elements of the lunar surface. The mission is considered to be a complete success. It was later revealed that the Soviet Luna 9 probe had used an inflatable balloon at the end of the landing in order to cushion the spacecraft's landing. While that allowed the first soft landing on the moon, it was never a practical system that could have been used for a manned program. That is to say, the Soviets were farther away from a successful manned mission to the moon than the Americans realized. In November 1969, Apollo 12 landed close enough to the landing site of Surveyor 3 that astronauts could walk to the spacecraft and recover parts from it that were then used to determine effects of 2.5 years of exposure on the moon's surface. NASA launched 7 Surveyor spacecraft, 5 of which had successful missions. Surveyors 2 and 5 crashed after technical difficulties. In all, the 5 successful missions operated on the moon for a total of 17 months, conducting important scientific experiments and investigating the chemical composition of the surface of the moon. Surveyor spacecraft managed a number of important firsts, including the first astronomical observations from the surface of the moon, the first color images of the Earth from the moon, and the first chemical analysis of lunar soil. Apollo 17 astronaut Harish Schmidt said of the Surveyor program, each of them was critical to the development of the Apollo spacecraft and equipment. Project Surveyor removed any doubt that it was possible for an American to land on the moon. I hope you enjoyed this episode of the History Guide, short snippets of forgotten history. And if you did enjoy, feed the algorithm by making a comment or clicking that like button. If you have suggestions for future episodes, please send those to our suggestions email box. Check out our webpage at thehistoryguide.net. And of course, we're on Facebook, Instagram, and Twitter. You can book a special message from the History Guy on Cameo and check out our merchandise at teespring.com. And if you'd like more episodes of Forgotten History, all you need to do is subscribe. It is June 13th, 2018, the 35th anniversary of a seminal event in human history. While it's little known and surprisingly forgotten, the event is a testament to human ingenuity, to human curiosity, to the human need to know where we fit into the vast cosmos. 35 years ago today, on June 13th, 1983, a plucky 569-pound champion that had already amassed an impressive string of firsts and was operating well beyond its life expectancy became the first man-made object to travel beyond the orbit of the outer planets of our solar system and head into the vast unknown. The journey of Pioneer 10 deserves to be remembered. The Pioneer program was a series of United States lunar and deep space probes launched between 1958 and 1978. Pioneer 4, launched in March of 1959, was the first U.S. probe to achieve escape velocity and successfully escape the Earth's gravity. A year later, Pioneer 5 investigated interplanetary space between the orbits of Earth and Venus, where it, among other accomplishments, confirmed the existence of planetary magnetic fields. Pioneers 6, 7, 8, and 9, launched between 1965 and 1968, represented a new generation of vehicles that were a series of solar-orbiting satellites designed to obtain measurements of interplanetary phenomena, to make the first detailed comprehensive measurements of the solar wind, solar magnetic field, and cosmic rays. The vehicles also acted as the world's first space-based solar weather network, providing practical data on solar storms which impact communications and power on Earth. The highly successful program has been touted as one of the least expensive of all NASA spacecraft programs in terms of scientific results per dollar spent. During the same period that they were launching Pioneers 6 through 9, NASA had been studying a concept for a space probe that they were calling the Galactic Jupiter Probe, or the Advanced Planetary Probe, that would study the solar, interplanetary, and galactic phenomena in the outer region of our solar system. NASA put together a proposal for a pair of probes that was approved in 1969, right at the heyday of the Apollo program. The two probes would be called Pioneer 10 and 11. The mission objectives were to explore the interplanetary medium past the orbit of Mars, study the asteroid belt and assess the possible hazard to spacecraft traveling through the belt, and explore Jupiter and its environment. These would be groundbreaking missions that would provide information critical to further deep space exploration. It was a tall order to develop a vehicle that was supposed to do many things no probe had ever done. The window to send a probe to Jupiter, when the relative positions of Earth and Jupiter permit such a launch at minimal energy, only occurs about every 13 months. As the missions were intended to lead the way for more planetary exploration later in the 1970s, the launch window for the first probe was set for 1972. That was a very brief time frame to design and build the craft. Moreover, the launch vehicle, an Atlas Centaur, set the upper limit for the vehicle's mass, which was not large, somewhere in the 550-pound range. Several steps were taken to help speed the program development. The project was assigned to NASA's Ames Research Center, which had experience with spin-stabilized craft, under the direction of Pioneer Program Manager Charlie Hall. The contract was given without a competitive bid, a choice that cut months out of the process, to TRW, which had built the Pioneer 6 to 9 vehicles. Basic design concepts followed a mantra of faster, better, cheaper. Whenever possible, the vehicle used modules and systems that were already tested, with most scientific modules based on the previous Pioneer designs. Redundancy was built into vital systems, with the craft designed to switch automatically to a backup should a primary system fail. A team of some of the world's best scientists winnowed down the options for experiments and instruments. In the era before microprocessors and integrated circuits, a true onboard computing system would have been both too heavy and needed too much power. A very simple processor that could store up to 5 commands directed the craft's operation, but most computations would be done on Earth. This simplified the design, but required that mission operators prepare commands long in advance of transmitting them to the probe. A particular challenge was power. The previous probes had all traveled roughly within the orbit of Mars, meaning they could get ample power from solar panels. But Pioneer 10 and 11 would be headed to Jupiter, where the sun produced 1/27th the light it does on Earth. That would require large and delicate solar panels. The answer was radioisotope thermoelectric generators. These devices generated electricity from thermocouples using the heat provided by small capsules of decaying plutonium-239. Referred to as Systems for Nuclear Auxiliary Power, or SNAP, such generators were generally considered unreliable for long-term use at the time. But the Atomic Energy Commission and the Teledyne Corporation had just designed a new version called the SNAP-19. In fact, they were anxious themselves to use the new design, and so covered the cost of building the prototypes. 4 SNAP-19 RTGs provided the power, placed at the ends of 10-foot booms to reduce the effect of the residual radiation of the devices on the probe's scientific instruments. The end result was an extraordinary design. Simple, durable, well-tested, yet elegant. But one more detail still had to be added. Eric Burgess, a journalist writing about the program, suggested to famed astronomer Carl Sagan that the spacecraft, which, if successful, would be the first to achieve escape velocity from the Earth's solar system, should include a message from mankind to any intelligent extraterrestrial life it might encounter. The result was the famed Pioneer plaque, designed by Sagan and astrophysicist Frank Drake. The 9-inch by 6-inch gold anodized aluminum plaque included figures of a man and woman, and diagrams that would provide intelligent life with information about the origin of the spacecraft, including the location of the Sun relative to the center of the galaxy and several known pulsars. Launched on March 3, 1972, Pioneer 10 passed the Moon just 11 hours from launch, making it the fastest human-made object ever at the time. On July 15, 1972, it became the first spacecraft to enter the asteroid belt, located between the orbits of Mars and Jupiter. No one knew what to expect. While NASA was confident the craft would miss any large objects, at the probe's velocity, a rock the size of a baseball would easily destroy Pioneer 10. The ship found that there were fewer particles than expected and passed through the belt safely, emerging in February of 1973. While its scientific instruments continued to gather data on the interplanetary environment, Pioneer 10 was now on the way to its primary target, the planet Jupiter. Jupiter has lethal radiation belts, and no one really knew what the effect would be. It might fry the tiny probe and all its scientific instruments. The craft did not have an actual camera. As Pioneer 10 passed by Jupiter and its moons in November, an instrument called an imaging photopolarimeter, which is used to measure an angle of rotation caused by passing polarized light through an optically active substance, measured the strength of sunlight scattered from the clouds of Jupiter and converted the information into digital representations of different shades of red and blue. With the aid of computers, scientists converted these signals into patterns of light and dark on a photographic film, making unique pictures of Jupiter and its moons that were displayed in real time. The pictures were so spectacular that the Pioneer Project won an Emmy Award for their presentation. Pioneer 10 had done its job, and as it slingshotted past Jupiter into deep space, the huge amount of data it provided was being analyzed to help refine the mission of its twin, Pioneer 11, already passing through the belt on its way to pass both Jupiter and Saturn. Pioneer 10's primary mission was completed, but the little probe that could wasn't finished yet. NASA extended its mission, hoping that its instruments could identify the heliopause, the boundary that marked the end of the Sun's influence, the true outer edge of our solar system. It passed through the orbit of Saturn in 1976 and Uranus in 1979. On June 13, 1983, 11 years after launch and a decade after accomplishing its primary mission of exploring Jupiter, the craft crossed the outer orbit of Neptune, at the time the outermost planet, and so became the first human-made object to leave the proximity of the major planets of our solar system. It was still loyally gathering and broadcasting data. In 1995, the RTGs of its twin, Pioneer 11, which had done spectacular flybys of Jupiter and Saturn, gave out. But Pioneer 10, well, pioneered on. NASA first tried to shut the program down in 1997, but the probe was still going, 25 years after launch. Diehards with the project managed to keep the program's life extended, first as a tool for deep space tracking exercise, and then as a test subject for a NASA study on weak signals. The craft, still going, was so old that the project managers had to keep an antique DEC PDP 1114 computer operating to send and receive commands. The last successful reception of telemetry from Pioneer 10 came April 27th of 2002, and the last very weak signal came January 23rd of 2003. NASA assumes that the RTGs are no longer producing enough power to operate the transmitter. At the time, the probe was some 12 billion kilometers away from Earth and had been loyally broadcasting from space for more than 30 years. And astoundingly, Pioneer 10 still had one more contribution to make. Pioneers 10 and 11 had, for reasons no one could explain, traveled some 3,000 kilometers per year less than they were predicted to have. The unexplained phenomenon suggested the possibility of some new physical principle. The mystery was called the Pioneer Anomaly. Only by reviewing the decades-old telemetry data from Pioneer 10 and 11 were scientists, in 2012, able to answer the question that heat from electrical currents in the craft was pushing back on the probes, causing them to decelerate slightly. Thus, the plucky Pioneer 10 made a last contribution to science 40 years after it was launched. Pioneer 10 led the way for the deep space missions that followed. Voyager 1, launched in 1977, is faster and has now gone farther than Pioneer 10, and was the first to cross the heliopause in August of 2012. Pioneer 10 was the first man-made object to go beyond Mars, the first to go through the asteroid belt, the first to swing by Jupiter, and 35 years ago today, the first man-made object to pass beyond the orbit of the major planets of our solar system. It deserves to be remembered. 38 years ago today, the entire world was looking to the sky. The event was worldwide news at the time, but it seems to have faded quickly from the public memory. And so today, on the anniversary of the day that it fell to Earth, the contributions of America's first manned space station, Skylab, deserve to be remembered. The idea for manned space stations actually started with military space stations. The idea would be to have a manned station that could be used for observation and spying, and perhaps even to shoot down enemy satellites. The United States proposed the Manned Orbital Laboratory Program in 1963, and the Soviets answered with the Salyut-Almaz program. The Soviets actually put manned military stations into space, but the enthusiasm on both sides waned as it became obvious that unmanned observation satellites were much more cost-effective. But both sides leveraged the idea in order to apply it to manned space stations for civilian research. In the United States, this is part of what was called the Apollo Applications Program, a program that was designed to leverage the technology that had been invented for the Apollo moon landing program, as well as to guarantee jobs for the people who had been trained for the Apollo program. The basic idea proposed by scientist Wernher von Braun was to use the cylindrical tube that was the second stage of a Saturn V rocket as a living space. The McDonnell Douglas Corporation was given a contract to do the appropriate modifications in 1969. And in 1970, NASA held a public contest to name the new station, and that's how the station got its name, Skylab. Skylab was the first time that NASA had to consider habitability. The previous manned space programs had all been short duration. The Apollo missions lasted less than 2 weeks. Astronauts would be expected to stay on Skylab for extended durations, requiring considerations for such things as living space and more palatable food. The final station would be about 282 feet long and hold 12,417 cubic feet of pressurized, habitable space. Skylab launched on May 14, 1973, but almost immediately things started going wrong. At the maximum point of vibration during the launch, an important heat shield broke off and tore with it one of the station's solar panels. When the station got into orbit, it turned out that damage from that accident prevented another of the solar panels from unfolding, and the station was dangerously underpowered. Turning the station so that the remaining solar panels could get more sun then caused the station to overheat because it had lost its heat shield. The mission to send astronauts to the space station, which was supposed to immediately follow the launch, had to be delayed 10 days as NASA came up with a repair plan. The crew of the first manned mission to Skylab, launched May 25, 1973, using an Apollo program command module, was sent with a repair plan. Mission Commander Charles Conrad said upon launch, "This is Skylab 2. We fix anything." They were able to effect repairs using innovative fix-it solutions and 2 unplanned spacewalks. It was, at the time, the largest such repair ever done in space. That experience produced the first lesson from Skylab. That unique ability of people to conduct unexpected repairs makes them invaluable to space exploration. Without the ability to send humans to effect repairs, the entire project would have been a loss. Skylab orbited the Earth from 1973 to 1979 and was occupied for a total of 171 days out of that time, with 3 manned missions, each exceeding the previous human record for days in space. In that time, astronauts performed 10 spacewalks, totaling 42 hours and 16 minutes. Skylab logged about 2,000 hours of scientific and medical experiments, making massive strides in observation of the sun, including the first videos of solar flares, as well as Earth observation that was previously impossible, producing a vast study of the Earth, its crops, weather, and changes in the environment. Crews manufactured alloys, grew perfect crystals, and learned to work in space. But the greatest contributions may have been in understanding manned space requirements. Astronauts in Skylab learned how to move, how to bathe in the first zero-gravity shower, how to cut their hair in space. They learned lessons about exercise and remaining fit that would be critical for future missions. There were ambitious plans to save Skylab for the future. The systems were still operational and ready for habitation in 1978, 4 years after the last manned mission to the station. The hope was to have the space shuttle program ready in time to have a mission to boost Skylab's orbit. But it was not to be. Greater than expected solar activity had warmed the atmosphere, increasing friction on the station and hastening its orbital decline. And the space shuttle program was behind schedule. On July 11th, 1979, Skylab, America's first manned space station, fell to Earth. NASA tried to use station telemetry to position the station to fall into the ocean off of South Africa, but it took longer to burn up than predicted, so some debris landed in Australia, but it caused no damage. When Skylab crashed to Earth in 1979, it was a worldwide event, but it was more of a celebration, really, than any kind of fear. One company sold an aerosol spray can that promised to be a Skylab repellent, and they promised a money-back guarantee if it didn't work. A town in Nebraska painted a huge target on the ground to give NASA something to aim at. A family in Western Australia won a $10,000 cash reward from a Philadelphia newspaper for being the first to recover pieces of Skylab. And a county in Australia fined NASA $400 for littering. Skylab was not the first manned space station in orbit. That honor actually went to the Soviet Salyut 1 station, but that was a troubled program. The first group of cosmonauts that were sent to Salyut 1 weren't even able to dock with the station and had to return to Earth unsuccessful. The second group managed to fix the docking problem and spent 3 weeks on Salyut 1, but then they were tragically killed in an accident on re-entry to Earth. The station was never used again. But still, in the Skylab era, the Soviets put up 6 different manned space stations. And after Skylab, the Soviets put up the Mir space station, where cosmonauts broke all of Skylab's records for the amount of time that a human spends in space. The Soviet experience was also critical to the lessons that were needed to be learned in order to provide a permanent human presence in space, a vision that has been realized with the International Space Station, which has been permanently manned since November of 2000. Still, Skylab played a critical part in the role of human space exploration and habitation. It was the station that proved that humans could live and work in space for a long time. It was the program that filled the gap between the Apollo program and the Space Shuttle program. That piece of time when NASA went from wow events to a going business concern. It was a pioneer in the human habitation of space, and it deserves to be remembered. In 1964, scientists at NASA's Jet Propulsion Laboratory noted that there would be a rare alignment of 4 planets, Jupiter, Saturn, Uranus, and Neptune, in the late 1970s that would give an unprecedented opportunity for a single spacecraft to explore more than one planet. NASA engineers began advocating for a program to build spacecraft to take advantage of this alignment and look at our solar system's outer planets in what they called the Grand Tour. That program would eventually become the Voyager program. 2 extraordinary spacecraft that gave we Earthlings not only a better look at the outer planets of our solar system, but our first real look at what lay beyond. Well, Voyager 1 was the first of the pair to encounter one of those planets, going by Jupiter in 1979, and the first to enter interstellar space in 2012. Voyager 2 was actually the first of the probes to be launched, and was the first, and to date only, spacecraft to visit our solar system's 2 ice giants, Neptune and Uranus. The extraordinary odyssey of Voyager 2 is history that deserves to be remembered. The rare opportunity provided by the unique planetary alignment had to do with a then relatively new concept called gravity assist. NASA engineer Gary Flandro, who holds the Bowling Chair of Excellence in Space Propulsion at the University of Tennessee Space Institute, explained in a 1966 paper in the journal Acta Astronautica. Contrary to popular belief, indirect ballistic trajectories involving close approach to one or more intermediate planets need not require longer flight duration than is characteristic of direct transfer orbits. In fact, significant reduction of both required flight time and launch energy results if efficient use is made of the energy which can be gained during a mid-course planetary encounter. Simply put, gravity assist uses gravity of a planetary body to help slingshot a spacecraft, giving it acceleration. The technique can be used to not just speed the spacecraft, but to allow methods of speed and direction change that do not require fuel, which is normally in short supply on a spacecraft that must carry all the fuel it needs for speeding up, slowing down, changing direction, or stabilizing the spacecraft. Assuming the craft has no ability to acquire more fuel, the mission must be carefully planned within the confines of the amount of fuel the spacecraft can carry, called the delta V budget. Delta V referring to the total energy needed for the spacecraft's change in velocity over the course of the mission. While the first theoretical papers discussing the concept were published in the 1920s and 30s, it wasn't until 1956 that Italian engineer Gaetano Crocco calculated a mission that would use multiple gravity assists, proposing a one-year exploration trip: Earth, Mars, Venus, Earth. The method of gravity assist was used in 1959 by the Soviet Luna 3 spacecraft, the first to photograph the far side of the moon. The craft used the moon's gravity to change the direction of the spacecraft. But there's a significant limit to the use of gravity assist, and that is the planetary body or large mass whose gravity you intend to use has to be in the correct place in order to direct your spacecraft to where you want it to go. How often that occurs depends upon the mission. It might be years in between times when planets align in such a way that you can use them to help get your spacecraft from one particular spot to another, and the proposed NASA Grand Tour is a relatively extreme case. The particular alignment that will allow the use of gravity assist to the outer planets being proposed occurs just once every 175 years. The same opportunity will not occur again until the middle 22nd century. This gave NASA a limited window of opportunity to get their craft together. The original NASA proposal was released in August 1969. They suggested 2 missions, each visiting 3 planets, including Pluto, still considered to be a planet at the time. One spacecraft would visit Jupiter, Saturn, and Pluto, the other Jupiter, Uranus, and Neptune. They proposed using an entirely new spacecraft, tentatively called the Thermoelectric Outer Planets Spacecraft, or TOPS, being designed at the Jet Propulsion Laboratory. But the estimated cost was high, as much as $1 billion, and the program had to compete with the new Space Shuttle program. Congress balked at the cost, and the mission had to be scaled back. Instead of an entirely new spacecraft, the missions would use one derived from the Mariner program, 10 spacecraft that had been launched between 1962 and 1973 to investigate Mars, Venus, and Mercury. Instead of the Grand Tour, 2 spacecraft would visit 1 planet each. This reduced the estimated cost to a more palatable $360 million per probe. But NASA was using a bit of an accounting trip because NASA was designing these 2 spacecraft with a mission life that would allow them to complete the originally envisioned Grand Tour, but only advertising visiting 2 planets, Saturn and Jupiter, in order to reduce the estimated mission costs. In 1977, the program was renamed Voyager. The probes would visit Jupiter, which had already been visited by Pioneer 10 and 11, and Saturn, which had been visited by Pioneer 11. In addition, the mission would allow a flyby investigation of Saturn's largest moon, Titan. Voyager 1 would be optimized for a visit to Titan, although there was an alternative option to visit Pluto instead. Titan, after being photographed by Pioneer 11, seemed to be more interesting. The second spacecraft, Voyager 2, would have options. The spacecraft would fly by Jupiter and Saturn, but could then continue to Uranus and Neptune. However, if Voyager 1 had not completed its objectives in its exploration of Titan, Voyager 2 could instead be redirected for another investigation of that moon instead of visiting the 2 ice giants. The 2 identical spacecraft would use 3-axis stabilization and a central parabolic antenna for communication. Attitude control was provided by 16 hydrazine fuel thrusters, and electrical power was provided by radioisotope thermoelectric generators, or RTGs. RTGs convert the heat released by the decay of radioactive material to generate electricity. This particular RTG designed for the Voyager program was the multi-100-watt radioisotope thermoelectric generator, or MHW, RTG, which produced 157 watts of electrical power initially, and halving that every 87.7 years. The craft carried 11 scientific instruments, and each also included a gold-plated copper golden record, a phonograph record that includes sounds and images intended to portray the diversity of life on Earth, and that, the hope is, could be deciphered by any intelligent civilization that might encounter the craft. In all, the Voyager spacecraft weighed 1,704 pounds. Because of their different trajectories, Voyager 2, using a longer circular trajectory aimed at the Grand Tour of the 4 giants, was launched before Voyager 1. Voyager 1 was optimized to visit Jupiter and Saturn and Titan, This plan allowed flexibility and redundancy. By launching Voyager 2 first, NASA had the option to redirect Voyager 1 to the Grand Tour if the first launch failed. And as Voyager 2 would not reach Saturn until 9 months after Voyager 1, there would be ample time to redirect Voyager 2 to Titan if Voyager 1 was not able to meet its mission objectives there. Voyager 2 was launched using a Titan III Centaur launch vehicle, a rocket that married the upper stage of a Centaur rocket to a Titan III rocket. The more than 1.3 million pound, or 637,000 kilogram rocket produced 5,339 kilonewtons of thrust. The spacecraft was launched from Space Launch Complex 41 in Cape Canaveral, Florida on August 20th, 1977, 2 weeks ahead of Voyager 1. Both launches were successful, but a near-fatal complication arose with Voyager 2 in April. The main radio receiver failed. The backup was functional, but a capacitor in it also failed. This meant that NASA had to communicate on a precise frequency, which was then affected by a number of factors. NASA engineers were forced to calculate the necessary frequency needed for each transmission to the probe. The ability to continue its mission was a testament both to the value of redundant systems and the ability of engineers to adapt to unexpected challenges. Voyager 2's close approach to Jupiter came in July 1979. Using its less circular trajectory, Voyager 1 had made its closest approach in January. While Voyager 1's closer approach to the planet allowed greater image resolution, it gave a relatively short window to the gas giant's moons, rings, and magnetic field. Voyager 2 did not fly as close to the planet, but its trajectory allowed a greater investigation of Jupiter's Jovian moons. The flyby also allowed a comparison of observations between the two probes, allowing scientists to, for example, confirm the eruption of volcanoes that had been observed by Voyager 1 on Jupiter's moon Io, the first time an active volcano was observed on a celestial body other than Earth. Voyager 2's closer observations of the moon Europa led to speculation that the moon is composed of water ice. Voyager 2 also identified 3 previously unknown moons of the system's largest planet. Voyager 1 flew by Saturn the following November, 1980. Its flyby of Titan met all its mission objectives, freeing Voyager 2 to continue with the Grand Tour. Voyager 2 started its encounter with Saturn in August 1981 and was able to use its antenna to take measurements of the planet's atmospheric pressure and density, as well as taking more photos of Saturn's moons. There was a brief issue with the probe's photography platform that endangered the rest of the mission, but NASA engineers were able to correct the problem. And while Voyager 1 headed off to deep space, Voyager 2 would be the first, and so far only, spacecraft to visit the Uranium system, which its closest approach occurring in January 1987, where it discovered 10 moons, 2 new rings, before heading to Neptune. At the time, because of Pluto's elliptical orbit, Neptune was the farthest known body in the solar system. Like Uranus, Voyager 2 is the only probe to have directly explored Neptune, where it confirmed 6 new moons and 4 previously unidentified rings. NASA explains that the planet was not quite what scientists expected. The planet itself was found to be more active than previously believed, with 680-mile or 1,100 km/h winds. Hydrogen was found to be the most common atmospheric element, although the abundant methane gave the planet its blue appearance. The close flyby of the planet allowed an understanding of the ice giant that could not be achieved using Earth-based observation. It was Voyager 2 that identified the large anticyclonic storm that makes up the planet's Great Dark Spot, called GDS 89, very similar to Jupiter's Red Spot and Saturn's Great White Spot. The encounter with Neptune was considered to be the end of Voyager's 2 original mission. NASA reported that through the end of the Neptune phase of the Voyager project, a total of $875 million have been expended for the construction, launch, and operations of both Voyager spacecraft. Of their mission to the outer planets, Arizona State University planetary scientist Jim Bell told Scientific American in 2015, "They were revolutionary. The Voyagers discovered many moons around the planets we never knew were there, and even the ones we knew were there were literally just points of light in telescopes before that. All of a sudden they changed to geologic objects, to worlds that had weather and volcanoes and tectonics. It was just night and day." And then, just like its sibling, Voyager 2 headed off into the vast unknown, and the mission was renamed the Voyager Interstellar Mission. The spacecraft passed through the heliopause, which marks the boundary between matter originating from the Sun and matter originating from the rest of the galaxy, thus putting Voyager 2 in interstellar space on November 5th, 2018, more than 6 years after its faster sibling did. A fact sheet provided by NASA's Jet Propulsion Laboratory explains, had the Voyager mission ended after the Jupiter and Saturn flybys alone, it still would have provided the material to rewrite astronomy textbooks. But having doubled their already ambitious itineraries, the Voyagers returned to Earth information over the years that has revolutionized the science of planetary astronomy, helping to resolve key questions while raising intriguing new ones about the origin and evolution of the planets in our solar system. After providing enormous amounts of information about the outer planets, both Voyager 1 and 2 continue to transmit data, giving new information and detecting some scientific surprises about the nature of the heliopause and interstellar space. As they travel, they encounter challenges, and the plutonium powering their batteries slowly decays. And as it does, various instruments are shut down, but Voyager 2 still has 5 scientific instruments operational, according to NASA. The two craft are moving in different directions, allowing them to collect data not just on interstellar space, but to compare data between the two locations. A 2019 edition of National Geographic quoted Princeton University postdoctoral researcher Jamie Rankin. "We have been interstellar travelers since Voyager 1 crossed, but now Voyager 2's cross is even more exciting because we can now compare two very different locations in the interstellar medium." A 2020 discovery of a new kind of solar electron burst prompted Iowa Today to proclaim, "More than 40 years since they were launched, the Voyager spacecraft are still making discoveries. The Voyager mission is now the longest running and most distant space mission in history." Last year, the only antenna on Earth, Australia's Deep Space Station 43, that is capable of communicating with Voyager 2, had to be taken down for renovation and repairs. While scientists could still receive data from Voyager 2, they could not send instructions for more than 8 months. But when the antenna was repaired enough to send instructions, after the longest pause in the program's history, Voyager 2 responded without incident, still soldiering on more than 44 years after being launched. Astronomy magazine noted in 2020 that both should be able to keep at least one scientific instrument running until 2025. And even after that, NASA expects to continue receiving engineering data from the probes until 2035, when they will exceed the range of the Deep Space Network antennas. The importance of the Voyager program is profound, both in terms of the science gained and in terms of the meaning of the accomplishment of sending an object made by humans so far from home. Thomas Zberchin, Associate Administrator for the Science Mission Directorate at NASA headquarters in Washington, D.C., said in a statement in August 2017, "I believe that few missions can ever match the achievements of the Voyager spacecraft during their 4 decades of exploration. They have educated us to the unknown wonders of the universe and truly inspired humanity to continue to explore our solar system and beyond." A 2017 edition of the magazine Futurism put it simply, "NASA's twin Voyager probes are the most important spacecraft ever launched."